This is problem set 36, where we're going to continue our discussion about enthalpy that we started in problem set 35. In this problem set, we're really going to get deep into how to calculate the enthalpy for a reaction. So before we get into that, just a little bit of a mini lecture. We're going to take advantage of the fact that enthalpy is a state function, and our goal is to calculate the enthalpy between our, instead of A and B, we're going to say reactants to products. Okay, and we want to find what is the delta H of this reaction as we go from reactants to products. We're going to take advantage of the fact that enthalpy is a state function, and we're going to take different paths to get from our reactants to products, and we're going to use the enthalpies of those paths in order to find the enthalpy change of our actual reaction. So there's three different paths that we're going to take. So the first path is to go from reactants to intermediates, meaning other molecules that we know the reactions for. We go from reactants to our intermediates to our products. There we're going to get a delta H1 there, delta H2 there. And we know that if we can get from reactants to intermediates and intermediates to products, then those delta H's will add up to the delta H of the whole reaction. Okay, so that is, let me move this down, reorganize a little bit. I'm trying to learn how to calculate delta H. There's going to be three paths. Okay, that is what I like to refer to as Hess's law. Okay, in Hess's law, we did a little bit of that in problem set 35, when you're given component reactions, and you can flip and scale those reactions in order to add up to the reaction that you care about. Okay, so I'm going to say manipulate reactions to add to desired reaction. And I think we might get the chance to do some of that in this problem set. If not, maybe not. Let's see. Nope, looks like not. So in that, because of that's the case, if you want to learn more about Hess's law, I would refer you to problem set 35. All right, a different path that we can take is to take our reactants and break them up into pure elements. We can take our reactants, split them all up into the pure elements that make up those reactants, and then take those pure elements and recombine them to make our products. And then if we can get the delta H of that process to split reactants into pure elements, and we get the delta H of the process to split pure elements into products, and we can add those up, that will give us the delta H of our overall reaction. Okay, the process of taking pure elements and making a product is called formation. And so I like to call this method using enthalpies of formation, which are delta H sub F. First, enthalpies of formation. We're going to talk more about what formation reactions are. Okay, but if we're trying to do enthalpies of formation, enthalpy of formation is the enthalpy to get from pure element to product. Okay, so if we're going from reactants to pure elements, that's going to be the opposite of forming, right? Those reactants are breaking up, and so instead of using enthalpies of formation for the reactants, we want to use the negative enthalpies of formation. So what we're going to end up with is the total enthalpy of a reaction. Total enthalpy change of a reaction is going to be the sum of the moles of product times the delta H formation of the product minus the sum of the moles of reactant times the delta H formation of the reactants. Again, we're forming our products, so we want to use the delta H of formation values for those. We're breaking up our reactants, so we want to use the opposite of the delta H of formation for our reactants. Again, you're going to see all of this done on this problem set. Okay, the third path is, instead of breaking into intermediate molecules or into pure elements, we're going to break into atoms. We're going to break apart everything. In other words, pure element, O2 is a pure element in its standard state. O is an atom. Okay, so we're going to break it down even further. And we get the delta H of breaking up reactants into all our atoms, delta H of creating all our products from our atoms. Then we can get the overall delta H. Okay. Now, taking our reactants into our atoms, we're going to have to cut every single bond or break every single bond. So we're going to need the energies associated with breaking each individual bond. And we call those bond enthalpies. Bond enthalpies. Okay, so bond enthalpies are the energy to break apart two atoms in a bond. So we're breaking apart our reactants. So we're going to count up all the bond enthalpies in our reactants, use those values, and then we're forming our products. So we're going to take the negative value of the bond enthalpies in the products. What that looks like is that the delta H of a reaction is going to equal the sum of N times the delta H of bonds in the reactants minus the sum of N times the delta H of the bonds in the products. Okay, this N just says you multiply by the number of bonds you have. In this case, you multiply by the number of molecules you have. So you see, because we're breaking our reactants, and bond enthalpies is the energy to break. So we want to use those values for our reactants. We're forming our products, so we want to negate the bond enthalpy value. Excuse me, I could feel the sneeze coming on. We need to negate the bond enthalpy values for the products because those are being formed, not broken. You'll also see this written as delta H of a reaction equals the sum of N times enthalpies of bonds broken minus N times enthalpies of bonds formed. Okay, so 3 different processes. They're each dependent on the fact that enthalpy is a state function. So the path to get from reactants to products doesn't matter. So Hess's law takes us through intermediate molecules using component reactions. Enthalpies of formation takes us down to pure elements and then back to products. Okay, and then bond enthalpies takes us down to atoms and back to products. Now you can solve for the enthalpy of any reaction using any of these 3 steps. It's just based off the information that you're given. That's how you decide which process to follow. And we'll see that today. Okay, so we are now going to take a minute and talk about delta H's of formation, okay, as that's one of these guys here, breaking our molecules into pure elements and reforming our products. So delta H of formation is the enthalpy of a formation reaction. So in this case, for which of these does delta H of the reaction, so delta H of this reaction, delta H of this reaction, right, for which of those does that represent a heat of formation? So really what this is asking is, which of these is a formation reaction? Okay. Well, you need 2 things to be a formation reaction. 1, you need to form 1 mole, and 2, you need to start with reactants or pure elements. So if we look here, number A, this forms 1 mole, and the reactants are pure elements in their standard state. So that is a formation reaction. Therefore, the delta H of this reaction is the delta H of formation of CO2, or the heat of formation of CO2. This forms 2 moles, so that doesn't work. This forms 2 different molecules, so that doesn't work. This forms 1 mole from pure elements. It's good. This forms 2 different products. That doesn't work. This forms 2 moles. That doesn't work. This forms 1 mole, but not from pure elements. So that doesn't work. This forms 2 moles, so that doesn't work. So only A and D, in this case, are formation reactions, and therefore in only A and D do the formation, do the heats of reaction equal the heat of formation. Hess's law. Oh, we will have an opportunity to use Hess's law. Okay, Hess's law can be used to find standard enthalpies of formation. PbO is the key component of automotive lead acid batteries and is also used extensively in making lead, glass, or SiO2 doped with PbO, which enables glass to block X-rays. Awesome. Write a balanced equation for the standard enthalpy of formation of PbO. Okay, so if we're going to do that, we're going to form 1 mole from pure elements, which will be Pb. And oxygen is not O, it comes as O2 in its standard state. So to make that balanced, we need 1/2 right there. Okay, we can't put a 2 here because that would be forming 2 moles, right? We need to form 1 mole, so we have to use a fractional coefficient there. So there's our formation reaction for PbO. So here, the delta H of this reaction will be the delta H of formation of PbO. Calculate the standard enthalpy of formation using the following information. So we're trying to find the enthalpy of formation of PbO, which is just the enthalpy of this reaction. And they're giving us component reactions. That tells me, because they're giving me component reactions, I'm going to use the Hess's law. I want to manipulate these to get this. So I need Pb on the left. I have Pb, but it's on the right. So I'm going to flip the equation. Okay, and when I flip the equation, I've got to flip the sign on the delta H. Okay, so now Pb is taken care of. 1/2 O2. The only oxygen here is on the left, which is where I want it, but there's 1 of them, and I need 1/2 of them. So I'm going to cut this whole equation by 2. In other words, I'm going to scale it down to 1/2 of what it was. And when I do that, the delta H of this new thing is going to be 1/2 of the old. Okay, so let's make sure everything works here. So I've got Pb on the left, 1/2 O2, 1/2 O2, PbO on the right, PbO on the right, and then C cancels C, CO cancels CO. So since these two equations add up to the one I want, these two enthalpies will add up to the enthalpy I want. So when I add them up, I get -218 kilojoules. So that means the delta H of this reaction goes -218 kilojoules, and since this reaction is the formation reaction for PbO, the delta H of formation of PbO equals -218 kilojoules. And you can say kilojoules per mole of PbO, and that's why we want to make sure we only make 1 mole of PbO. Great. Okay, CaCO3 is the main component of seashells. Write the balanced equation for the standard enthalpy of formation of CaO. Okay, so CaCO3 comes from Ca and C and O2. We need 3 O's, 3/2 O2. That's the formation equation for CaCO3. Calculate the standard enthalpy of formation using the following information. Now in this case, what do they give us? In this case, they give us enthalpies of formation. Here they gave us equations. Here they give us enthalpies of formation. So we're not going to use Hess's law here. We're going to use our enthalpies of formation. Again, remembering the delta H of any reaction, is the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So if I were to write that out, right, the delta H of this reaction is going to equal the enthalpy of formation of my products, so CaO plus CO2 minus the enthalpy of formation of my reactant. Okay. They tell us the overall delta H of this equation, this reaction. So we know this guy. They give us the enthalpy of formation of CaO and CO2, and they ask for that one. So we are in good shape. We only have one unknown variable, so we can plug things in. The other thing to make sure is each of these enthalpies of formation needs to be multiplied by the stoichiometric coefficient, but they're each 1. So we'll see a situation later where they're not. So we get CaO is negative 635.5 kilojoules plus negative 393.5 kilojoules minus delta H of formation of CaCO3. Okay, so now I can just solve there. I get with the delta H of formation, my unknown variable of CaCO3 is negative 1207 kilojoules per mole, which, if I cared, well, I guess I do care. That means that the enthalpy of this reaction is negative 1207 kilojoules per mole, because this reaction is the formation reaction of CaCO3. All right, C. CO is a pigment in ceramics and is involved in the process of making rayon. Write the balanced equation for the standard enthalpy of formation from CuO. All right, let me read that again. Write the balanced equation for the standard enthalpy of formation of CuO. Okay, so we're making CuO, 1 mole, and it's pure elements. Copper plus 1/2 O2. And calculate the standard enthalpy of formation using the following information. Okay, they give us an enthalpy of formation. They give us the overall, so we're going to do something very similar to last time. We know that the delta H of this reaction is going to be enthalpies of formation of products minus enthalpies of formation of reactants. Okay, let's make sure we have what we need. We are looking for enthalpy of formation of CuO. We're looking for the enthalpy of that reaction, right? They give us the overall, they give us water, and they've left out copper and hydrogen. Okay, so here is an important thing to know and to understand, is that enthalpies of formation of pure elements in their standard state are 0. And why is that? Let's look at H2, for example. If I wanted the enthalpy of formation of H2, what's the formation equation look like for H2? Making 1 mole of H2 from pure elements in their standard state. So you can see there's no change there. So for pure elements in their standard state, the delta H of formation is 0. So we actually do have copper and hydrogen. So we can go ahead and solve this. Copper is 0. H2O is negative 5.8 kilojoules. Minus, this is what we're looking for, plus 0. And I get that the delta H of formation CuO is negative 156.1 kilojoules. There you have it. So that is the enthalpy of that reaction. Again, because that reaction is the formation reaction of CuO, so the delta H of that reaction is the delta H of formation of CuO. All right, number 3. That was a long 2 problems. Number 3, calculate the delta H for the combustion of ethanol. Combustion of ethanol, what's that equation? We got C2H5OH. I'm adding O2 to make CO2 and water. I need 3 of these. I need 2 of these. So I need 3 of those. Okay, so they give me here delta H is a formation. Delta H formation again are products minus reactants. So my delta H in my reaction is going to equal sum of N times delta H of formation of products minus the sum of N times delta H of formation reactants. My products are two CO2s, plus 3 waters. And then my reactants are 1 ethanol and 3 oxygens. Oxygen's a pure element at standard state, so 0 for the delta H of formation. Okay, plug those in my calculator. And I get that the delta H of this reaction is negative 1367.2 kilojoules for that reaction. Okay, they gave me delta H as a formation, so I'm going to do products minus reactants. Fertilizer, ammonium nitrate, and fuel oil, a mixture of long-chain hydrocarbons similar to decane, can form an explosive mixture. Determine the enthalpy change of the following explosive reaction by using the appropriate enthalpies of formation in Appendix 4. So they say enthalpies of formation. Appendix 4 is in the back of your book probably, so you can find it there. You can also just Google them. And we want to find the delta H of this reaction. They tell us to use enthalpies of formation, so we're going to be doing products minus reactants. So my products, I've got 3 nitrogens. Nitrogen's a pure element, so that's 0. 17 waters. And we actually used water up here, didn't we? They give us water was negative 285.8. And 10 CO2s. They said CO2 up here is negative 393.5. Minus my reactants. So I need the value for NH4NO3, which, if you look up, you will get, got 3 of them, negative 365.6 is what I got. My other reactant is C10H22, which they give me is 249.7. Plus my 14 oxygens, which will be 0 kilojoules per mole because they're a pure element in its standard state. All right, there we have it. So just do all the math. Plug that in one more time. Did I miss something? That's my mistake. So I used this value for water, but this is vapor water, and I used the value for liquid water. So I'm getting my answers a little wrong. So if I look up the value for liquid water, it is actually, sorry, for gas water, it's actually negative 241.8. What am I doing wrong? Let's see. Just plug it in one more time, make sure. Okay. There it is. There, we got it. Just type it in my calculator wrong. So the delta H of this reaction is going to be negative 7198 kilojoules. There you go. So using enthalpies of formation again, products minus reactants. All right, number 5. Use the bond enthalpies in the table above to estimate the enthalpy change in the reaction below. Okay, so they're now telling us to use bond enthalpies. Remember, with bond enthalpies, the idea is we're taking our reactants, breaking them into atoms, and then forming our products. Bond enthalpies are defined as the energy to break a bond. So we want to use the given value for our reactants and take the negative value for our products. So we end up with this delta H for reaction will be the bonds broken, the reactants minus the bonds formed, the products. So I look here, say what's being, well, let me write here, delta H of reaction equals the sum of the enthalpies of the bonds broken minus the sum of the enthalpies of the bonds formed. So the delta H reaction is going to be broken. What's breaking? Breaking NH, 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 NH. So I've got 4 NHs, which are each 391. Okay, I'm also breaking an NN, which is 163. That's what I'm breaking. What am I forming? Forming an NN triple bond, which is 941. And I'm forming 2 HH bonds, which are 436. Which gets me the delta H of this reaction is negative 86 kilojoules. Now, one thing to note, when it comes to what's more accurate, bond enthalpies is the least accurate way of finding the delta H for a reaction. The reason is the energy to break a CC bond is different in different molecules. And so these are average bond enthalpies. The average CC bond, for example, takes 348 kilojoules per mole to break. But for that reason, because they're averages, these are the least accurate, but still pretty good. All right, using the bond enthalpies, estimate delta H reaction for the reaction of ethane with oxygen gas to form CO2 and water. So ethane, C2H6, plus O2 makes CO2 and water. Let's balance it. I need 2 of those, 3 of those, 4, 7 halves of those. I want one thing for ethane. When we talk about combustion, we like to only burn 1 mole if possible. Okay, so let's look at what these molecules look like. We're going to have CCHH. And O2 looks like that. CO2 looks like that. And H2O, whoops, looks like that. All right, so again, we want the sum of the bonds broken minus the sum of the bonds formed. What's breaking? I'm breaking 1, 2, 3, 4, 5, 6 CH bonds. CH bond is 413. I'm breaking 1 CC bond, which is 348. I'm breaking 7/2, right, because that's 7/2 OO double bonds. OO double bond is 495. It's breaking. Now what am I forming? I'm forming 2 CO2s, which gives me a total of 4 CO double bonds. 799. And I'm forming 3 waters, which gives me a total of 6 OH bonds. 463. Okay. And I get the delta H of that reaction is negative 2831. Nope, that was double. Negative 1415.5 kilojoules per, yes, kilojoules. I could also say kilojoules per mole of ethane, because my reaction was for 1 mole of ethane. But saying just kilojoules is also just fine. Use the bond enthalpies to estimate following reaction. Chlorine gas, chlorine's diatomic, reacts with ethene. Ethene is C2H4 to form 1,2-dichloroethane. Okay, you don't know what that is, but it looks like this. And this is C double bond C, H, 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 Cl, Cl. So we're doing the same thing, broken minus formed. So delta H of this reaction, what's breaking? We've got a Cl-Cl bond, which is 242. Is it balanced? Yeah, it's balanced. We've got 4 CH bonds, which are each 413. We've got a CC double bond, (614). That's everything that's breaking. What's forming? Sorry, minus. What's forming? We got 2 CCLs, 328. We've got 1 CC, which I think is 348. And we've got 4 CHs, which are each 413. Broken minus formed. That's how we do bond enthalpies. I get that the delta H of the reaction is negative 148 kilojoules. There we go. So that's some extensive practice with bond enthalpies. Six, use bond enthalpies to estimate delta H of reaction for the Haber process below in which nitrogen from the air is fixed into usable form. Compare this with delta H, the reaction calculated from delta H formation. They give you the delta H formation of NH3. Is there a difference? Why is there a difference? Which do you expect to be more accurate and why? Okay, so we've got N2, H2, and H3. Bond enthalpies will be broken minus formed. We are breaking an N triple bond, which is 941. We're breaking 3 HH single bonds, which are 436. We're forming 3 NH single bonds, which are 391. Oh, plus this is a minus. What am I doing wrong? Oh, there's 2 NH3s, so there's really 6. There we go. When I do that, I get a delta H of reaction of negative 97 kilojoules. How does that compare to this? Well, it's like more than double. But actually it's not, because the delta H of formation is negative 46.19 kilojoules per mole of NH3. We made 2 moles of NH3. So if we want to get ours per mole of NH3, we need to divide by 2. Now we can compare and we get negative 48.5 kilojoules per mole of NH3. So now how do they compare? They're a lot closer. But are they still different? Absolutely. And which one's more accurate? This one is more accurate. So delta H of formation is more accurate. Than bond enthalpies. Because again, bond enthalpies are average values. You see that on this table right here. These are average bond enthalpies. Because different, CH bond in one molecule will be a different bond enthalpy slightly than a CH bond in a different molecule. All right, listed below are molar enthalpies of combustion for several fuels. These values provide a measure of the energy available to harness by burning the fuel. However, since we don't purchase fuels by the mole, we purchase them by mass or volume. A better way of comparing them is to use a fuel value. A fuel value is simply heat of combustion in kilojoules per gram instead of kilojoules per mole. Calculate the fuel value of each of the following compounds from the heats of combustion and state which fuel has the highest energy density. So we're trying to get kilojoules per mole into kilojoules per gram. Okay, so we've got negative 286 kilojoules per mole. And for hydrogen, 1 mole is 2 grams. Gives me a value of 143 kilojoules per gram. Now technically it's negative 143 because the energy is being released, right? But fuel values just typically are always given as positive values. So there we go. Methane. Methane, 1 mole, 16 grams. Gives me 50.1 kilojoules per gram. Ethanol. Ethanol has a molar mass of 45 grams. ethanol, C2H6O. 46 grams. Ethane. Ethane is C2H6. It's 30. .9, just using molar masses here. Propane. Propane is C3H8. Butane. Butane is C4H10. Which gives me 45.8. And lastly, octane. Octane is C8H18. There we go. So we had our fuel values in kilojoules per mole, or I guess we had our enthalpies in kilojoules per mole. We converted them all to kilojoules per gram. It wants to know state which fuel has the highest energy density. That would be hydrogen by a long shot because it is so light. All right, so that was our second problem set about enthalpy. Keys to take away here is there's 3 ways to calculate enthalpy. One is using Hess's law, where they give you a couple of reactions, 2 or 3 reactions, and you have to add them up to the one you want. Okay, then we have enthalpies of formation, okay, which if you are given those, you can do products minus reactants to find the enthalpy of a reaction. And then we have bond enthalpies, where you can do bonds broken minus bonds formed to find the enthalpy of a reaction.